In this video, we will define the concept of a space with functions. Well, we have some intuition of spaces with functions. So if you have any topological space X, then you can look at, for each open subset U in X, the collection of all continuous maps from U into whatever space you want. It could be the real numbers, for instance. So we have our topological space X, and let's say it's the space X, and then you have mappings to the real number line, and we know that, so in addition, for every open set U, we have continuous maps from U into R. And let's pay attention to the mappings. We know that if you have U is a subset of X, then you get a map from the set of continuous maps from X into R to the set of continuous maps from U into R, because you can restrict, right? If you have a function from X into R and the subset U, then you can restrict. So the restriction of F from X into R is just F restricted to U. And we know that the restriction of a continuous map is continuous. And more generally, suppose, so that's one thing we know. And we also know that if U is the union of a family of open sets, and F is continuous on U, then F is continuous on U, then the restriction of F to U alpha is continuous on each U alpha, and conversely, right? If F is continuous, F is such that the restriction U alpha is continuous for all U alpha, then F is continuous. Okay, we also know that if F is continuous on an open set U, then the set of elements of U such that f of U is not 0 is open in U, and therefore it's open in X because U is open. And in addition, the function 1 over f is continuous on this set. So let's call this set D of f. It's continuous on D of f. So this is the prototype of a space of functions. So in this case, we looked at, for each open subset, all continuous functions from U into R. Now we can generalize this. So more generally, we can define a space of functions. So let's say that K is a field. Then, definition. So a space with functions is a topological space X together with the assignment to each open subset U of X. So together with the assignment to each open subset U of a K algebra, which we'll call K bracket U of K-valued functions on U. So, well, I'm not done with the definition, but so far we are looking at K-valued functions on U, but a K algebra of them. So it doesn't have to be all continuous K-valued functions on U. I mean, they don't even have to be continuous. It's just some K algebra, okay, which we call K of U. And we call these regular functions. Okay, so we have something like this, and they have to satisfy the following conditions. So the first one is let U be the union of U alpha of a family of open subsets, and let F be a K-valued function on U, then F is regular if and only if the restriction to alpha is regular for each alpha. So that's the first condition. Then the second condition is suppose that F is a regular function on an open subset U. Then if you look at the set, so D of F, which is defined to be the collection of U in U such that F of U is not 0, this set is open, and furthermore, 1 over f is regular on D of f. Okay, so in the previous example, so this generalizes the example we had above, because in the previous example, we took K of U to be the set of all continuous maps from U into K, where K was, so in the example we took K to be R or C, but it didn't have to be, we took it to be R, but it could be taken to be any field. Okay, it's just that R has a topology, so so here we don't necessarily have continuous maps, because our K, we don't necessarily have a natural topology on K. So we have regular, we have K of U, a subalgebra of K-valued functions on U, and then we call them regular, and the regular maps are required to satisfy certain compatibilities. So that's what a space of functions is. It's a generalization of the concept of a topological space with continuous functions.